work is joule. The SI unit of work is a joule.
Okay, I'm gonna write that down. Thank you.
And based upon this equation here, there we go, this equation here, it should also balance. So the unit of work should be the same unit as kinetic energy is. Kinetic energy, 1/2 mv squared, should have the units of mass times the units of speed squared. The 1/2 does not contribute to the units. So this is a kilogram times a meter per second squared, which is a kilogram meter per second squared times meter. And that, by definition, is a Newton. So the units of work and the units of kinetic energy both come down to Newton meters, which is a joule.
Oh, okay. So if we're finding work and you say give us a unit, we would give you joules.
More than likely.
Okay.
If we started out with international standard units, yes.
Over here in America, they do work in hours.
Now, let me make this more complicated for just a moment. You really don't have to worry about what I'm about to say next for a couple of chapters. There's also something later on that we'll come across known as torque. Torque also has the units of Newton meters. But when talking about torque, the Newton meters does not equal a joule. So Newton meters equals a joule when talking about work and energy.
Torque deals with how much force is placed on. I remember my dad was putting a winch on his truck, and he had to adjust the torque of a bolt to a certain, it was like 4,000. He called it nanometers, but I don't think that's right.
Yeah,
I think it was Newton meters. He just was confused. But
Dads, gosh, come on.
It in essence, is it just saying how much force is applied from one object to another to secure it?
The difference is, it's actually, just as a force is a push or pull, torque is more of a twist or turn. So
Okay.
it's how much is trying to turn something.
Okay.
The influence, which might cause angular acceleration. That's a couple chapters away.
Okay.
Foot-pounds you often hear in this country.
Foot bounds?
Foot-pounds.
Foot pounds. Okay.
So pound for force, foot for
Okay.
displacement. What was I going to do before I did the unit thing? So work. Oh, different types of force. Oh, actually, one more thing before I get onto it. So I have to have some required audience participation.
We need those applause signs and stuff.
Maybe we'll just slip it into the video so that when people are watching it at home.
Yeah. Soundtrack of like laughter from a sitcom happens.
Sorry, my mind just shot off in a not nice place. All right, so from now on, if I ask you, what's the formula for kinetic energy? Your response is?
1/2 mv squared.
Absolutely.
Okay.
Now, what I want, and I am serious about this, in unison, I want all of you to participate. I'm about to ask you what's the formula for kinetic energy, and all of you, in unison, are supposed to say 1/2 mv squared. Don't embellish. Don't say 1/2 times mass times the speed squared, just 1/2 mv squared. There's usually one in the crowd. All right. What's the formula for kinetic energy?
1/2 mv squared.
That's the chorus of angels I always want. Now, the reason why this is the one formula I definitely want you to have memorized so that 30 years from now, sure, let's assume I'm still up and about. 30 years from now, I run across you in the street and we first go through the, wait a second, I know you from somewhere. I should be able to ask you what's the formula for kinetic energy, and you should know 1/2 mv squared.
Because of course, the first thing you're gonna ask us is not, how are you doing? It's gonna be, what's the kinetic.
At some point in the conversation, I'm expecting to get to this.
Okay.
Hey, we go over the important stuff first, okay?
This isn't important?
No, I'm saying like, this is the important stuff.
Now, why do I want you to have this memorized as opposed to all the others? Almost every formula that we deal with in this class is classical mechanics. F equals ma is actually a specific case. We'll get to a slightly more generalized case when we get to momentum. But that's the formula for kinetic energy. You're working on your Nobel Prize winning dissertation, or work, it doesn't actually have to be a dissertation, but you're working on your Nobel Prize winning work in physics. That's the formula for kinetic energy. All the rest of them you have to start tweaking them. Now later on, it's going to seem like I contradict myself when I say, hey, there's rotational kinetic energy, which is 1/2 I omega squared. At that point, it's legitimate for you to go, wait a second, I thought you said that's the formula for kinetic energy. We have to somehow deal with the issues later on of, if we have an object where not everything is traveling the same speed, such as if I'm closing the door, not every part of the door is traveling the same speed. How do you deal with that? That's at the root of it.
Centripetal force.
So what's the formula for kinetic energy?
1/2 mv squared.
I heard some enthusiasm in there, so let's work on the rest of it. Now, different types of force. I'm not talking about F-tom or additional type forces that way. I'm talking about those can be broken up into 1 or 2 categories. There's conservative force. And a conservative force does conservative work. I'm just going to abbreviate that. And if it's not conservative, they got clever, it's non-conservative.
What's the difference?
I'm glad you asked. And that produces non-conservative work, that's the difference. One produces conservative work, the other one does non-conservative work. What's the difference? All right, there is a formal definition for conservative work. If I expose an object to a conservative force, and it does a round trip, it starts in one spot, it ends up back in the same spot. If the kinetic energy is the same at the beginning and the end, that's a conservative force. So for example, if I take this marker and I throw it up into the air, when it gets back to the starting point, just after it left my hand, before it touches my hand, when it gets back to the starting point, it should be going the exact same speed as it did to start with. This gravitational force is a conservative force. Now, there's a formality that in the calculus space class, I would write up the formal definition of conservative force. For this, I'm going to give you a list of all the conservative forces we've covered so far. Done. Weight is included. Weight is a special case of gravitational force. It does count. So weight or the generic force due to gravity is a conservative force, and that's our entire list up to here. Later on, we will add elastic force.
You said the definition of conservative force was when the object travels at the same speed or the same space?
Under the influence of that force. If I have an object that is experiencing a conservative force, when it gets back to where it started, it will be going the same speed as when it left.
Okay, because I was about to write velocity, but that makes no sense.
What is it?
Wait, so basically, like conservative force is like when it's a constant force.
No. In the example that I gave, yes, gravitational force was constant. As I throw this up and comes back down, or close enough to constant. Gravitational force comes up, comes back down. It's basically the weight doesn't change in that small duration. But as we get to elastic force, that's if I have a spring. If I stretch a spring out, I attach a mass to a spring and I stretch it out and I let go. When it gets back to where it started, it's going the same speed as when it began. And so an ideal elastic force, it's not a constant force because as the spring contracts and expands, the force varies. I just find it a whole lot easier to go with, we got the list. Is it on the list? Conservative. If it's not on the list, not conservative.
So is it like, under the same conditions, it will apply the same, like, situation? Like, if you have two scenarios with the exact same conditions, you would expect them to have the same answer, whereas a non-conservative force doesn't necessarily?
I think to some extent that's valid. Probably have to throw in a lot more words to make it precise. Brooke?
What is elastic force? Like, I know what elasticity is, but
Spring, an ideal spring, I attach a mass to a spring and it will oscillate back and forth, and at any point in here, it will always be going the same speed.
okay.
So whenever it reaches that height again, or if I keep it vertically or horizontally, whenever it reaches some position, it always has the same speed at that position.
So does elastic force ignore gravity?
No,
Oh,
but in that case, if I have the vertical situation where I've got the mass, say, an ideal spring, I attach a mass to it and I let it oscillate up and
it would
down.
eventually stop.
There's two conservative forces acting on it.
Right.
Now, it will not
Okay.
stop ideally. But the reason it would stop would be for things other than those two forces.
Okay.
Like permanently stop. Obviously, when it turns around, it stops momentarily.
Right. Because I'm thinking if you put a mass on a spring and it's vertical, it'll eventually stop
It will be, but there's other things involved, some
because of that mass.
non-conservative forces.
Yeah, right. Okay. So what's a non-conservative force?
Friction. Friction's a classic. Friction, normal force, tension.
Is it just when an object is not traveling at the same speed at the beginning and end? Like you said?
Yeah, I mean,
it's,
pretty much.
Okay.
So it's not consistent.
It's not, I think I agree with that.
Yeah.
It's not guaranteed.
That's what I'm just trying to find a kind of like a synonym of the conservative and non-conservative, you know what I mean?
To some extent, and I haven't got the formal wording down yet, but to some extent, the conservative forces seem to be natural.
Okay.
That normal, of course, then you get into, is a spring really natural? Yes, it is, apparently by my definition. Gravitational force, electric force, magnetic force, these are all conservative forces.
Okay.
Electric and magnetic, physics 152. In 151, that's it. See, I'm suddenly thinking of all these ways that I'm poking holes in my own definition, but
Gotcha. But you would say that non-conservative is synonymous with non-consistent.
it feels like yes, but I haven't thought through that
Yeah.
long enough.
If we were to build a whole list of non-conservative forces, we'd probably find possibly one, if I had to guess.
Yeah, I would not be surprised.
Okay.
All right. Now, why is it called conservative and non-conservative?
Because they said so.
Because
More than that.
non-conservative forces convert their energy into other things, perhaps? Like they lose it through their heat or through sound.
Okay. Non-conservative forces transfer energy from one object to another. Conservative forces transfer energy from one form to another. That's one form of energy to another. Because kinetic is just scratching the surface. There's actually three major types of energy. And then there's other vocabulary which science classes like to throw in there just to make it more confusing.
Is this the difference between potential and kinetic energy, or is that different?
The potential is another form.
Okay.
A conservative force can change energy from kinetic to potential or potential to kinetic.
Okay.
Wait, so there's more to just the kinetic energy and
Oh yeah, there's three major kinds.
is kinetic and potential two of those?
Yes.
Okay.
Those are the two that we really care about for this course, but there's a third one that I will introduce. It doesn't really have much importance until we get to the end of Physics 152.
Static?
Is it static or is that the same as potential?
Static energy,
Yeah.
I'm not sure what static energy is. Like static electricity?
No, like something's not moving, but that would be potential.
That's
Yeah,
basically
potential.
potential.
Well, let's talk about what the three types are. So we have kinetic, potential, and rest. Potentially, that's what you're thinking of,
Yeah.
possibly.
Kind of-
All right, so if you think about classical physics, all objects have speed, position, and mass. This is the energy of speed. This is the energy of position. And the rest is the energy of mass, technically rest mass. So kinetic energy, 1/2 mv squared. If speed is not zero, there's kinetic energy. Potential energy, there's not a formula for potential energy.
Okay.
If I ask you what's the formula for potential energy, the proper response is which one?
Oh.
So what's the formula for potential energy?
Which
one?
I'm glad you asked. It turns out that every conservative force has a potential energy formula. I will eventually derive at least one of these. So if we're talking about gravitational force of weight, the potential energy formula is mgh plus a constant.
What's the H?
Height. We'll definitely get into more detail, just laying out a whole lot of stuff that seems completely separate. If we're talking about generic gravitational force, in other words, the big G and 1 m2 over r squared, the potential energy formula is negative big G mass 1 mass 2 over r, not r squared. Although at some point, I will put a square down at the bottom, and you're supposed to correct me when I do that. Elastic force, the potential energy associated with that is 1/2 lowercase k delta x squared.
And those are all potential energy.
Those are all potential energy. Oh, and they're all plus a constant. Plus a constant.
What's the constant?
Whatever you want it to be.
Wouldn't it be gravity in these cases? Nope, because we've already got gravity.
Yeah, gravity is of course.
You generally pick a constant so that the potential energy equals 0 where it's really convenient.
Oh, okay, so like, if your gravitational force was negative, you'd wanna add a constant to it to make it like close to 0.
Possibly. So if I drop an object and I want to know what the potential energy here and the potential energy at the ground, it's usually convenient to make the ground 0.
Right.
So you officially add a constant so that potential energy is 0 at the ground.
Okay.
Or you might make potential energy, add a constant so the potential energy up here is 0. Ultimately, what matters is the change in potential energy, not the actual value itself. So if I'm looking at the change in potential energy, the constant's going to cancel out.
Okay.
Ian?
So will we include like chemical energy under potential energy?
All right,
Or
yes.
should we ignore that because it doesn't?
Chemical energy typically falls under potential. Sometimes I'll see heat energy, which is actually a type of kinetic. And so all the other types of energies that are introduced fall into one of these three categories. I have not seen an exception yet. Although I'm sure there's somebody out there who needed to publish a paper, so they made up something. Because ultimately, a lot of the stuff feels made up. All right, rest energy. Most of you know the formula. Although if I just said write down the formula, most of you I suspect would blank. I can start you out though. E equals,
MC squared.
so rest energy, E sub R, is equal to m sub 0 c squared. The difference between what you said and what this is there's a little subscript here. Rest mass is the mass of an object when it is at rest relative to the observer.
What is E?
Energy.
Energy,
So it's
Okay.
with a subscript R.
just
Oh,
like
okay.
is this just like the energy that is contained in the atoms of the thing, or?
Yeah, so if I needed to create matter out of nothingness,
Right.
that is the minimum amount of energy. Assuming absolutely no loss of 100% efficient system, that is the amount of energy I need in order to create an object.
Right.
Or, if such a thing were possible, that's the amount of energy I could get out if I could somehow turn that object into pure energy.
So energy equals mass times C is.
The speed of light.
Speed of light.
Oh. And the speed of light would just tell us how fast the reaction goes?
No, it's
Meters
that,
per second.
there's some videos I got out there where I go through the long derivation of it.
Gotcha.
It's a really fun derivation. The first time I actually did it in front of a class, well, actually the first time I kept messing up, so that was horrible. The first time I did it, sort of start to finish with minimum number of mistakes,
Yeah.
2.5 hours.
To derive the E equals mc squared?
Yeah.
You did this in front of a class,
Oh yeah,
so they just like.
they
Watch the
were enthralled. Their speechlessness, I assume, was just they were so rapt they forgot how to speak.
Yeah.
Just sat and watched.
Yeah.
Man, right.
You can imagine how exciting that was. I'm not gonna subject you to that. All right, so rest energy we only care about if we have something bursting into flames. The math, because if I light a match, if I somehow took a mass, incredibly accurate scale reading, balance reading, I found the mass of an unlit match, I then strike it, making sure any parts of the